everyone. Uh, Welcome to the sixth talk of our vertex series. Today we have Saraswata Sensarma from BMAT third year. And we will talk about topics.
Thank you so much, Vikram. I think it might be the seventh talk, but yeah, chalo. So, what is coupling? Coupling is a tool used a lot in problems. It's a very simple, even you can even call it a trick, but it's like $1 million trick. It solves many problems in one go, and choosing the right coupling is often gives a very short and sleek answer to many problems arising in discrete probability, in control theory, in all kinds of things. Okay, so I'll give a short talk on that. So the notion of coupling is very simple. Let's say we have two probability measures, mu and nu, on different probability spaces. This is sort of the crux. You have two measures on different probability spaces. A coupling of the two measures is simply a joint measure on the product space omega 1 cross omega 2, such that mu and nu are the respective marginals. In other words, this holds. So you have any sets A and B in omega 1, the marginals are mu and nu. Okay. So for instance, if you have two random variables, a coupling will be a random vector such that the marginals x hat and y hat have the same distributions as x and y. So one point to be noted, throughout most of the talk we'll be just talking about discrete measures, measures on countable spaces or even finite spaces. So if you are not comfortable with idea of measure, just think of these as PMFs, mu and nu as PMFs on the spaces omega 1 and omega 2. Okay, and the random variables as discrete random variables.
That should be omega 1.
Hmm?
Second leg, omega 1 means this method.
Yeah, this would be omega 1. I'm sorry. Yeah. So this is omega 1. So, of course, you can have examples of coupling. For instance, the most trivial example is the independent coupling. So, you create this random vector x hat and y hat such that x and y are independent, and you put the standard CDF, that is the product of the two CDFs. There are, of course, other examples. I'm sure all of you know that knowing the marginals does not specify the joint distribution. There is a lot more to the story. For instance, another example would be, let's say you have two Bernoulli random variables, P and Q, where P is, say, strictly smaller than Q. Then you can define a coupling in the following manner. So let's say U is a uniform 0, 1 random variable. You define x hat and y hat as these, that if U goes above a level 1 minus P, which has probability P, then you say x hat is 1, otherwise it's 0. Similarly for y hat. It's easy to see that x hat and y hat are distributed as Bernoulli P and Q respectively. So x hat y hat is a coupling of x and y. Yeah, and well, this fact wasn't really needed. So the whole point behind coupling is when you have two different random variables, note that x and y were defined on very different probability spaces. They were not comparable. However, the moment you have this coupling x hat y hat, you preserve almost all of the properties of the random variables, but define them on the same probability space. Here, which is defined as a space of this uniform random 0, a uniform 0, 1 random variable. You define them on the same space, and that allows you to compare them in some sense. Okay. So we'll be looking at, that's all about coupling. That's the definition. So now we'll be looking at some nice places where coupling is used. First one being the connectivity of random graphs. Let's say consider any graph G, which is say a priori connected, and fix P in between 0, 1 and define this random graph GP by simply looking at each edge and keeping that edge with probability P or removing that edge from the graph GP with probability 1 minus P. Do this independently for all edges. Okay. So once you do that, you get this edge set. So basically what you're doing is you're defining independent IID Bernoulli P random variables to each edge, and you're keeping that edge. This is the edge set of the graph GP. So you're keeping that edge if XE is 1 or removing that edge if XE is 0. So the question is, well, GP can be connected. GP might not be connected. If you sort of remove all the edges, it won't be connected. Question is how likely it is it to be connected? Our intuition tells us as P increases, the probability of GP being connected should be larger and larger because more and more edges are starting to come into the picture. But how do you formalize it? So if you try to do this proof, you would realize very quickly that there is one problem. The problem is this GP and GQ are not comparable in the sense they are defined on different probability spaces. You cannot directly say that GP is a subset of GQ. So that coupling helps us solve that problem using almost exactly the example we saw, the monotonic coupling. So let's say fix P less than Q and consider UE to be ID 01, ID uniform 01 random variables associated to each edge E of our original graph. So then you define the G hat in the following manner. You look at those vertices where this U is greater than 1 minus R. The probability of this happening is R. And since uh, you only include those edges which satisfy this property. So G hat R is exactly the same construction as G of R, which we saw before. It's just formalized in a different manner. However, since we have replaced the Bernoulli 01 random variables, the Bernoulli random variables with uniform 01 random variables, we can now compare them. Notice that an edge is there in G. If there's an edge in G hat P, the corresponding edge must be there in G hat Q. So for P less than Q, the edge set of G hat P is contained in the edge set of G hat Q. In particular, the probability of GP being connected is the same as probability G hat P being connected. It's the same thing, but now we have this relation because if a subset is connected, the graph is connected, and that completes it. So you see the crux of the matter was always defining them on the same probability space, and then the problem becomes trivial. So coupling in this manner sometimes helps serve as an aid to our intuition that okay, we feel this intuitively is true, but we can't really compare them. Somehow find a way to define them on the same probability space, then compare them, and then you're done. Fine. So this was like the first most simple example, most prototypical example of what coupling is and what coupling does. So the second is bounding the mixing times of Markov chains. So uh, this will sort of be an addendum to Dipto's talk that was given yesterday. So we recall something called the total variation distance. Let's say you have two measures, probability measures mu and nu. You can define this total variation distance as how much the measures mu and nu can differ for a single event. There is one problem here. There should be a modulus. Okay, there's a small mistake. So how much the probability measures mu and nu can differ for a single event. In fact, you can easily show a nice closed form expression. This is getting supreme over set, so it's a bit weird to think about. But this has a very nice expression. In fact, it's half of the L1 norm between the measures mu and nu. These are just sort of recalling. That's a way of measuring the distance between two measures. Now, if you have two measures which are far apart, and if I tell you I give you a coupling of the same, it shouldn't be the case that x is equal to y for a. So this is another way of thinking about this total variation distance is consider any arbitrary coupling of the two measures mu and nu. Then there is a lower bound to the probability that x equal to y. So this one way of interpreting this was how much they can differ on a single event. And this is another way of interpreting it. For any coupling, they differ by the probability that x and y differ is at least this distance, total variation distance. The proof is actually extremely simple. You just write the mu a and mu a and split these up into two events, x equal to y and x not equal to y, and then do the proof. It's extremely simple. In fact, there exists a maximal coupling. That is, there exists a coupling of x and y such that this equality holds. Okay, so that's called the maximal coupling, and you can find the maximal coupling by looking at when this inequality becomes an equality. That's a very simple exercise, but I won't do it here. Now the question is, what about Markov chains? So consider a Markov chain xt with on the state space chi with transition matrix P, and the stationary distribution is pi. So we know this theorem from the previous talk that if mu t is the distribution of the at tth time, that is xt, and if the Markov chain is irreducible and aperiodic, also called ergodic, then pi t converges to the stationary distribution. First of all, the stationary distribution is unique because it's irreducible, and secondly, the pi t will converge to pi. So this gives a nice notion of ergodicity, sort of this, so that even though it's a random process, eventually you approach a nice behavior. The question is, whenever you have convergence, you ask what rate it converges in. So to quantify the rate, you can define this distance. The distance between this might be, you can replace it by mu naught, but it doesn't matter. So you look at the distance between the distribution at th step starting from mu and the stationary distribution for all mu. Look at the maximum over all mu. And this dt goes to 0. That is precisely the convergence theorem. Now you define the mixing time as the first time where this dt goes smaller than some epsilon, some fixed epsilon. And you can sort of When I just say mixing time, I mean epsilon equal to 1/4 for technical reasons. It doesn't really matter. But this quantity is sort of a bit hard to get hang of because this pi might not be known. You might not know the stationary distribution, and it's a bit hard to compute. It doesn't just depend on matrix P. So you can define another distance, d bar, as in the Th step, you just look at this is the xth row of P to the power T, this is the yth row of P to the power T. You just look at the total variation distance between these rows, and eventually this also goes to 0. Okay, so in fact, this d of t and d bar of t are very close to each other. They differ only by a constant factor. This is the proof is using triangle inequality. You can, I'm sure you can do it. You can just see it from here. So basically, this means that if you know d bar t well enough, you know dt, and if you know dt well enough, you know d bar.
One thing,
Yeah.
it will be like D and D bar will change in the last.
Here?
Because look at D bar, if you can use the
No, I think it's this way only. Yeah, because if I just write here, I think it's this way because ptx dot pi. Oh no, I think you're right. I think you're right. Yeah. So just interchange this d bar and d. I'm sorry, but anyway, my point stands that if you know d bar, you know d, and if you know d, you know d bar well enough, up to only a constant factor. So the point is, how do you bound this mixing time back up? So this go back here. This is exactly the form where we have the coupling inequality, distance between two probability distributions. So in particular, let's say you have a coupling xt of the Markov chain. That is, you have a coupling of the random variables xt and yt at each step, and they start from 2 points x and y. So at each time t, the distributions of xt and yt are precisely ptx dot and pty dot by the construction of Markov chains. So by the coupling inequality, you have this result. But now what do? You know what d bar is, so just maximize over x and y, and you get d bar. So now have a look. This quantity d bar is very important. If you want to find the mixing time, you want to get a good hang of what the function d is. And instead of doing that, you can get a good hang on what this function d bar is. The question is, point is, if you that point settles, that boils down to effectively choosing a nice coupling so that this maximum is low enough and you get close to equality. So that's what I was talking about. That often problems boil down to choosing the correct coupling, and then you'll get a nice bound on this d bar. And that's what many probability theorists try to do, is finding the correct construction of coupling. So yeah, you can give nice bounds to T mix if you choose this d bar well enough. We take the example that was considered in the last talk. Consider a hypercube graph, which is basically just n tuples of zeros and ones, binary n tuples. And on this graph, x is connected to y if and only if they differ at exactly one coordinate. Okay, so in 3 dimensions, it's just the cube. In 2 dimensions, it's the square. In higher dimensions, I don't think you can imagine it, but yeah. So we consider the simple Resi random walk on H. That is, we start from a point with half probability we stay at that point. We don't move anywhere. And with the other half probability, we go to one of the edges, go through one of the n edges uniformly at random. In other words, we flip one of those binary entries uniformly at random. Okay. The transition matrix for this chain is of course like this. And now we construct this. It's not really important, the form of the matrix. You want to construct a coupling xyt of this chain started at xy. Well, we start there, and at each step, what we do is initially it's x0 equals x and y0 equal to y. So we at each step, at each time t, we choose a coordinate uniformly at random from 1 to n, and generate a random variable, a Bernoulli half random variable, which is 0 with probability half and 1 with probability half. And then we just update the kth entry of both xt and yt. Now, doing this, you would see that the Markov chain that you get, the marginal Markov chains that you get for xt and yt are precisely the original random walks on a hypercube, because zt could be equal to xt or could be equal, the kth coordinate of z could be equal to the kth coordinate of x or vice versa. I mean, the z could be equal to kth coordinate of x or not equal to, with probably half each. So, but now consider this. Since we have updated the random variables xt and yt in the same manner, if tau be the first time where till which every coordinate has been chosen, x tau would be equal to y tau because we have updated them in the same manner. In particular, this d bar of t, which was maximum over x and y of probability that xt is not equal to yt, is simply it's bounded above by the probability that tau is greater than. But what is this tau? This tau is a very well-known object. For people who know, it's the coupon collector random variable. So the situation is you have n coupons in a box, and you draw one of them uniformly at random and put that back in the box. Tau is the time till which you have, by which you have seen all the coupons. Okay. So this is the stopping time for the coupon collector process that has been very well studied. In fact, this is a very easy bound to put. It just follows from union bound. Some of you can take that as an exercise, and this immediately gives that the mixing time takes this. It's at least this is bounded above by this. Now, for the people who will attend the next talk, a small spoiler: this is not the best bound. The coupling we chose was a way too simple. We couldn't really give a nice bound, but it was simple to sort of describe. There'll be a half in front, but at least it gets the order right. The correct order is t mix less than equal to half log n plus some constant into n. Anyway, so that is all about mixing times that I wanted to say. Coupling is used in a lot of other places, and the next example that I want to focus on is the idea of stochastic domination. Let's say you have two. Now, I'm sure you might have seen this example. Let's play a game. Let's say you have two dice. Dice one, let's just call them 1 and 2. Okay. So then, more likely than not, you just roll the dice, and the player who gets the higher number wins. The dice which comes up with a higher number wins. You can give construction such that dice 1 beats dice 2 more often than not. Dice 2 beats dice 3 more often than not. Dice 3 beats dice 4 more often than not. But dice 4 beats dice 1 more often than not. So there is a cycling. This beating more often than not is not exactly an ordering. Being larger than so probability x greater than y being larger than half is not an exact ordering of Markov chains. This is not transitive. However, of probability distribution, it's not transitive. However, there is an ordering which is transitive, and that is what we'll talk about here. This gives a partial order on the set of all probability distributions. So we look at the notion of stochastic distribution, domination. Let's say we have two random variables x and y. We say x dominates y. If for every fixed x in R, the probability that x is larger than x is greater than the probability that y is larger than x. So x would be large for any fixed point. The probability that x is larger than the point is larger than the probability y is larger than that point. This is denoted in this form. So in other words, if we just look at the CDFs of x and y, the CDF of x is always smaller than the CDF of y for each x. So here are some examples you can easily see. The first one is easy to see. You can just compare the CDFs. The second one actually is not so easy to see. It's comparing the CDF is hard. In this case, there are only 3 values. There it takes countably many values. So we'll give a simple way of proving this as well. But that already points out the problem. You cannot really say when two random variables are when one random variable stochastically dominates the other. You need some sort of characterization of this, and that is what we provide here. Let's say you have two random variables x and y. So x stochastically dominates y if and only if for every increasing function f, expectation fx is strictly larger than expectation of fy. But where does coupling come in? Right here. So there exists a coupling x hat y hat, some sort of a coupling, such that x hat is almost surely larger than y hat. That, to me, when I first heard it, was surprising. So if you want to look at the proof, 3 implies 2 and 2 implies 1 is very simple. You have to choose the right function in this setting. And it's very intuitive as well. So if x hat is always larger than y hat, then expectation of fx hat is larger than expectation of fy hat, but x hat and y hat are the same thing. So when you take the expectation, it doesn't really change anything, and so on. It's a very simple proof. However, the question is, 1 implies 3. How do you prove it? But that is exactly the same construction we discussed way at the beginning for Bernoulli random variables. Let's say x hat. So fix a random variable u from uniform 0, 1 and define x hat to be fx inverse of u and y hat to be fy inverse of u. As all of you know, that this construction would give that x hat has the same distribution as x and y hat has the same distribution as y. And by the increasing nature, because x stochastically dominates y, we know that fx is always smaller than fy. In particular, fx inverse is larger than fxy. and that would give us this result. So by the way, we have taken it as a generalized inverse, uh, taking the supremum, which you can always do for increasing functions. So that completes the proof. So this gives you a nice way to think about stochastic domination. Is in some probability space, you can take the image of this two random variables, and one would always be larger than the other. So, and another, this also characterization also gives another use of stochastic domination. Let's say you have a random variable x, which is dominated by y, but you don't know much about x, but you do know some things about y. In particular, all the moments of x will be lower bounded by the moments of y, exponential moments, any increasing function this way. So, stochastic domination gives a lot of control on random variables if you know it. Okay, and this by this construction, you can actually see that the result we saw in the last slide, Poisson will hold. Poisson lambda less than Poisson mu when lambda is less than mu. Okay, so such a coupling is called monotonic coupling, uh, for which this holds. Okay, so now the question is, are we for coupling for random stochastic domination for random variables is good enough, but we go to our graph, okay, GP. We saw that probability that GP is connected is an increasing function of P. In fact, this holds for any increasing graph property. If Q is any increasing graph property, then probability that GP is in GQ in Q is always an increasing function of P. How do you? Also, we were able to construct give the exact same construction. We were able to construct a monotonic coupling of GP and GQ in some sense. So the question arises: can we interpret it in somehow? You look at the previous characterizations, and you see that almost all of them are here. So the question is, in some sense, can we say that GP is dominated by GQ when P is less than P? So this quickly suggests a generalization of the notion of stochastic domination to posets. So you don't need the entire ordered structure of R, but you need some sort of a partial order. Now we'll be dealing with chi-valued random variables, where chi is a poset. So a poset is just a set with a less than equal to, which satisfies reflexivity, antisymmetricity, and transitiveness. And let's say x comma chi is a poset, then we say a function is increasing if fx less than equal to xy, fy, whenever x is comparable to y and x is smaller than y. Okay, and an event is said to be increasing. Event just means a subset of x. A subset is said to be increasing if whenever you have x, you have all the values which are comparable to x and larger than x. They are also in this setting. And for measures mu and nu on this random variable on this space x or chi, whatever you want to say, we say that mu dominates mu if for any increasing set mu a is greater than mu a. If you go back to the to our case of real valued random variables instead of kite value, you would see taking a to be all the values larger than x would actually satisfy this property. That was our definition of stochastic domination. And often the generalizing an idea just boils down to making the right definitions. And these definitions give us precisely the same characterization that we had before. That is, if you have two random variables y, which are taking values in a finite poset, chi, then the same characterization holds. Again, 3 implies 1 implies 2, 3 implies 2 implies 1 is the exact same proof. It's the same thing. There's nothing different. The question is, you want to prove 1 implies 3 again. So, by the way, I forgot to mention this talk will be a little bit proof heavy because at the end of the day, coupling is a technique. I want to show you how the technique is used in various fields. Okay, so this will be a bit proof heavy, but I think the proofs are simple and very nice. So you can, in fact, this theorem is called Strasson's theorem. Strasson gave it in his paper in I think 1960s. You can extend it to posets of the to any poset where chi is a finite separable metric space, also called a Polish space, and the less than equal to is a closed partial order. We won't be doing that. We'll just be doing the finite case. And the proof that we use here, that we give here, uses the maximum interval. So, what does it really mean for our random for a random for a probability distribution nu to be a joint measure of mu and nu? The marginals must match. This is the precise expression for that. Also, we want to construct a nu such that x is always larger than y. In other words, we have to have mu xy is 0 unless x is larger than y. Okay, even if they are uncomparable, we want to have them to be 0. So this set of equations suggests a very nice network flow interpretation, which is via this graph. Okay, you take this graph, you have sources, this network, you have source S, sink T, and you have, so let's say our metric space chi is x1 through xn. Then you can define these vertices x1 through xn and x1 prime through xn prime, and you join them to S, and you join these vertices, say xi to xj prime, only when xi is larger than xj. Okay, these are the only edges that you put. So yeah, and these edges will have infinite capacity. We don't really care what capacity we put. We just make it large enough. And these edges we put precisely the capacities mu x x1 so mu x x, and these the capacities mu y. So one thing is clear: if you can find the flow of flow strength 1, you would be done. Mu xy would precisely be the flows on the edges joining x and y. Yeah. So, and for that we go to the maximum min cut here and we try to find what the minimal cut is. Okay. So look at this cut. A cut basically is a collection of edges, removing which the points S and T would be separated. Okay. So for instance, if you remove all of these points, this is your cut, and the capacity of this cut is the sum of the capacities of all of these edges. Okay. So this is a cut of capacity 1. Of course, if you want any legitimate cut, you want to minimize the capacity, you cannot have any of these green edges, they have infinite capacity. So the question is how to find the minimal cut. I claim that this is the minimal cut, one of the minimal cuts. Well, let's say you have any cut, and A be the set of vertices that you in the process of making the cut that you have disconnected from S, and B be the set of vertices that you have disconnected from T. Fine. But note one thing, that all the vertices that you have not disconnected have edges to themselves. Okay, x is less than equal to x trivially, so they have edges to themselves. In particular, this B must account for all of those. That is, since C is a cut, the A complement set must be contained in B. And the moment you have that, you're done, because the capacity is just the sum of capacities of these edges. It will be mu xa plus mu ib, but B contains A complement, so this is the case. But the moment you see A complement, and you can like do a bit more tweaking to show that this holds for mu x as well, and that would give you, yeah, that's it. So this particular step I haven't justified, but it's justified in, you can one line and you can just try it if you want. Yeah. All right. So now the question arises: we talked about stochastic domination on sets, on posets, in fact. So the question is, why do we need such a thing? One notion is you want to define some sort of partial order of the random of measures, probability measures. That is fine, all fine and good. The question is, why do we really care about stochastic domination? And if you have been with us for all this time, you'll be rewarded with three, I think they're nice examples. So let's say X can be a tight sequence of random variables. And when I say tight, I simply mean that uh, for all, if you fix any epsilon, for any epsilon positive, there exists a set of this form, minus m to m, a compact set, such that all of these values, uh, so all of these values lie in this set M for all n. This has a high probability. For each epsilon, you can find such an M such that this. That is what we mean by tight. Just intuitively, just means that these random variables don't increase to infinity. They are bounded in some sense. That's all it means. So whenever you have a uh, bounded sequence of real numbers, you know that they converge. Because bounded monotonic sequence, you know that they converge. The question is, can the same thing hold for random variables? The answer is yes. So if this happens, then xn goes in distribution to x for some random variable x. For the people who have seen a little bit of probability theory, and in fact, you can put some more conditions. I haven't done it. You can put slightly more conditions and make this convergence go almost sure. For the people who have done a little bit of theory, proving almost sure convergence is a nightmare sometimes. And having such a relation gives you enormous power. For instance, take this example, Poisson lambda. If lambda goes to lambda naught, Poisson lambda will go to Poisson lambda naught. You can, yeah. So proving this on its own is okay. in this case might be maybe simple because the function values are nice and easy, but in general it's not so easy. So now the second application is the law of large numbers. We'll present a quick generalization of the law of large numbers. So consider a sequence xn of independent but not identically distributed Bernoulli random variables, such that xi is Bernoulli pi. So we know that if xi is are all Bernoulli p and they are independent, of course, then Sn by n, this limit exists. In fact, you don't care about not just the limit. So the limit exists and would equal p almost surely. However, let's say the p's are not fixed; they are varying a little bit, and let's say p star is the suprema, is the lim sup of these pi's. Then, if you look at this, is the empirical mean of the Bernoulli random variables. The lim sup of the empirical mean would also be bounded above by the p star. In fact, we have a similar result for lim inf. The inequality just goes the other way. And with both of these results, if you have Pn goes to P, the lim sup and lim inf are equal, then Sn by n is P. So all you want is a sequence going to P. You don't really want a constant sequence of P's. That's the generalization of the law, the strong law of large numbers. Okay. So we'll give a quick proof of this, and this would imply this proof is the exact same, and that would imply the remaining. Okay, so by this time, all of you are familiar with exactly how to do the proof. You define, by the way, coupling is not just uniform random variables. Okay, I haven't given other examples, but you can have a lot. So you define the monotonic coupling again. So you take un to be the fnx inverse. So fn is just the Bernoulli pn, whatever the distribution of xn is. So you do this so that un becomes IID uniform 0, 1. There's one mistake. This won't be fnx inverse. Okay, this would just be fn. I'm sorry. So you can do that, and that will give you a un, which will be IID uniform 0, 1, and fix any p slightly larger than our lim sup p star, and define xn prime in this manner and Sn to be in this manner. Now, then if you look at the sums, Sn will not differ. Sn will be less than equal to Sn prime, except when it's not. But this set when it's not, when pi is larger than p, since p is larger than the lim sup, this set is finite. So if you take the limit, this term drops off, and you get this. But this one we know, Sn prime we know, Sn prime every random variable is IID uniform 0 p, IID Bernoulli p, so this holds. But epsilon is arbitrary, so we are done. And the proof for in the element is similar. Huh? Huh? Sorry? No. I'm sorry. Xn prime is also Bernoulli p. Another mistake, I think. It would be larger than 1 minus p instead of being p. Many mistakes, but I hope you get the idea. This because this is Bernoulli 1 minus p instead of being Bernoulli p. But anyway, so you get the notion of lim sup, and lim inf, the proof is exactly the same. You take something smaller and you go on. So that gives a nice proof. So I mean, somehow I find this very cute that even if you're the first example of law of large numbers was you have to have everything IID and everything has to have same distribution. Not really important. The important part is the independence. Even that you can relax, but relaxing that is a little bit harder. You have to use Borel-Cantelli lemma and other things. But relaxing the identically distribution is the quite simple, as you might see. And another application is a small generalization of the central limit. With the same setup as before, we want to have something like this. Okay, but what do? You define Sn prime. Sn prime we had was Bernoulli p. So for Sn prime, this holds. So if you subtract those two equations, you need something like this. This should go to 0 almost surely. That's what you need. But this goes to 0 almost surely. So basically, you want Sn minus S to decay faster than square root of n. In other words, that will happen if you take the expectation. If the expectation goes to 0 almost surely, that is, expectation of Sn minus Sn prime should be little o of square root n. If that holds, then we are done. But you have this very simple inequality that you use triangle inequality here, and you just observe that xn minus xn prime is always smaller than 1. You put this inequality, and then you're done. So connect it, just check once because some sort of sound. I think it's fine. So another sufficient condition would be this. So note that this is a bit stronger than simply Pn going to P. For instance, if you take something like this, Pn to be P plus 1 over square root n, this would not hold. Then the sum would be of the order of square root n and not smaller than the order of square root n, and this condition wouldn't imply the convergence. Yeah. So that's about it for the talk. I think I finished very early, but it's there. But yeah, there's a what? Yes. So there's a lot more. I just focused on this idea of stochastic domination with and showed some little bit of applications to make things, but there's a lot more that you can do. Coupling is a very universal trick. I can call it a trick if I want to, but it has wonderful uses in these places. How much time do I have? I have 15 minutes. Okay, then I might try to go into some of these applications on the board instead of, yeah. So one of the applications is a Poisson approximation of the and the Stein-Chen method for the Poisson random variable. So all of us know that appropriately defined a sum of binomial random variables, or just appropriately defined a sum of Bernoulli random variables goes to Poisson. Right, that will be a binomial random variable, and that would go to Poisson. Question is, what is the rate of convergence in that sense? So if you have a practical problem and you want to approximate a binomial random variable using a Poisson random variable, how close are your approximations when you have a given n and you have given probabilities? The answer is again given by a coupling argument, and that gives the notion of Poisson approximation of the binomial or the Bernoulli, and that would very quickly give a nice characterization of the so-called Stein-Chen method of the Poisson random variable. The Stein-Chen method is a characterization. Let's say you have a sequence of random variables xn. When does xn converge to a Poisson random variable? It gives a nice condition for that, which is sort of easy to check. Instead of being in terms of the random variable, it's in terms of expectation of the random variable, which is a lot easier quantity to handle because it's not random. Okay. So that is one example. The second example is positive correlation of measures. This is a huge part of probability theory, and with many applications. So you have something called Harris inequality, something called FKG inequality, and Holly's inequality. Now, what are these? Okay, I might try to actually, these are done. So let's erase them off. Talk a little bit about these. These find uh, extensive use in percolation theory, random matrix theory, and I mean not that much random matrix theory, sorry, but in random cluster models and so on and so forth. These have many applications. So when I write this Poisson approximation, this has a very nice application as well. For instance, let's go to this example, an example of random graphs. So let's say you have a random graph, Erdős-Rényi random graph, which is just, since I've already defined that, you have a complete graph Kn, and you're looking at Kn of P. You're choosing each edge with probability P, or not choosing it with probability 1 minus P. What is the degree sequence in this setting? So as it turns out, if you replace P by lambda over n and take n goes to infinity, the average degree of each vertex is lambda. It's easy to see. The average degree of each vertex would just be, I mean, the degree. Okay, let's fix a vertex. What is the let's fix a vertex V. What is the degree of V? The degree of V would precisely be all, there are n minus 1 edges going out of V, and each of them is there with probability P, is not there with probability 1 minus P, independent of each other. So the degree is precisely binomial n minus 1 comma P, which is lambda over n, which you can easily see goes to in distribution to Poisson lambda. Right. So the average degree is lambda. In fact, you can just show that all the moments are the same and so on and so forth. Now the question is, what about if I ask a slightly different question? What proportion of vertices will have, say, a degree d? And this is apparently a much harder question, because here this is a local phenomenon. You are talking about one vertex. I'm asking you a global phenomenon. I'm talking about what proportion of vertices have degree d, what proportion of vertices have degree 0, say that they're isolated, and so on and so forth. And that is done using this first method. I won't be giving you the proof, but hopefully this example is interesting enough so that you go and check. And if you look at this, this is the number of vertices of degree d for a given graph divided by the total number of vertices. This also goes to the moments of Poisson d. So this goes to e to the minus d, what is lambda to the d by d factorial. So if you just look at the proportion of vertices, they also follow a Poisson and lambda distribution. This is sort of a this is a nice application of this Poisson approximation. If you're interested, I'll give the references. So that is an example I wanted to show. I didn't give the proof. The proof is 2 pages long, but the idea is not that hard. And the positive correlation of measures, I'm not talking about that too much, but it has wonderful applications in percolation theory and random cluster models, even in random graphs. Okay. Another part which I won't spend time on this, but is the theory of Markov decision processes. So Markov decision processes are something like this. You have a Markov chain, but not exactly a Markov chain. So somebody can come in and tweak the Markov chain at each time t. So that will give a Markov decision process. So you take the decision based on some other behavior that okay, I will tweak the Markov chain in a certain way. Now, why is this sort of idea of monotone control or some coupling useful? Because we know that convergence results become nice and simple when you're dealing with monotonic processes. If they are increasing, they have a very nice convergence structure, and you can prove convergence results in a much easier fashion. So if you have a Markov decision process and you tweak the Markov processes each step in a certain way such that the resulting chain becomes monotonic, then convergence results are very easy to get. And that is the theory of monotone optimal control. I won't be talking about it, but it's a very sort of interesting thing to look at. Another example I just came up with it is using the so-called optimal transport. Okay, so the idea of optimal transport, this is the so-called Cantor-Lewis formulation of optimal transport. Let's say you have a sand pile which has this distribution, sand pile of mass 1, which is distributed like this, and you want to move the sand pile, move it such that it looks like this. Okay, so you somehow want to translate each particle here and create something like this, but you want to do it with minimal cost. You don't want to spend too much time. So a particle that's already here, maybe you just keep it there, and so you want to minimize the amount of things you have to move. This is the question of optimal transport. How do you actually transport things optimally from one place to another? And this is the so-called Cantor-Lewis formulation. Let's say this, okay, I'm taking the mass to be 1. So let's say the distribution is some mu, and this distribution is some mu. All I want is basically, let's say c x comma y is the cost function of moving one unit of thing from x to y, from a position x to a position y. Let's say I'm moving a thing from here to there. That is the cost. Then the cost in total moving would simply be an integral over how much stuff, let's say, okay, I'm writing it this way, cxy dx dy, integral over appropriate space. It doesn't matter here, it's just r. But nu xy is the amount of stuff that I pick up from x and move to y, and this is the corresponding cost. So this will be the total cost. However, what do I want? I want the initially to be in this form and the final thing to be in this form. In other words, this is the marginals. So nu, I defined it. So let's call them mu1 and mu2. So I want mu1 and mu2 to be the marginals of this distribution. And to find the optimal cost is simply finding the coupling nu such that this is minimized. So optimal cost is simply a minimization problem over the space of all couplings. This is a coupling of say mu1 and mu2 such of over this integral. That is great. So this sort of connects what we were doing to what people in optimal transport do. For instance, one example might be uh, uh, in our case, if we know that mu1 is dominated by mu2, this optimal coupling we have actually just computed using our Strassman's theorem. I'll leave you to think about it. But this, all of this goes to show that the notion of coupling is useful in many places because it's a very basic fundamental notion. It's all about asking whether, if you have two random variables, whether you can define them on the same space meaningfully. So that's about it. I don't have anything more to say. And here are the references. So this is a nice reference on the coupling method. This is an entire lecture note, which is of, I think, 93 pages on the coupling method, just various applications of coupling. This actually goes into good details about the things, the parts that I missed, the FKG measures and positive correlation inequalities. And this one by Lindvall is an entire book of 263 pages on the coupling method. So that just goes to show how far reaching applications coupling has. And this is another nice toolkit. And this one is where you can find the more about the ideas of monotone control and so on and so forth, and more details of stochastic ordering and more ways of characterizing and determining whether something has an order or not. So that's about it. Thank you so much.
So, anybody has any questions? So let's thank the speaker once again.
Thank you so much. The next talk will be in a few minutes, and that will be given by Sanchan Bowal of third year, of MAth first year, sorry. And that will sort of be a continuation of what the last talk was, okay, on mixing times, and he will explain a phenomenon called cutoff. Thank you so much.